Hello, everyone. Today, I'm so glad to be here to present our work, Stealthy Low Earth Orbit Satellite to Ground Quantum Communication. My name is Guanqun from the Ohio State University, working with my advisor, Ting Zhu. Our research addresses a critical vulnerability in satellite-based quantum key distribution and propose a novel defense framework that ensures robust, resilient quantum communication without modifying quantum hardware. Let me start with some background. Quantum key distribution, or QKD, is a method of securely sharing encryption keys between two parties using photons to transmit quantum information. It leverages the fundamental principles of quantum to provide information theoretic security. Any eavesdropping attempt introduces detectable disturbance in the quantum state. Security guarantees has propelled QKD from theoretical concept to the practical deployment. And today, satellite-based quantum key distribution represents a transformative advancement in the global secure communication. By leveraging low Earth orbit satellites, quantum signals can travel through the vacuum of space, enabling low loss and stable transmission across the continent and oceans. And several experimental demonstrations have already shown the quantum key distribution over distance exceeding 1,200 kilometers, and establishing the state's QKD as a realistic and an important building block for the future global quantum network. But the technical feasibility alone does not guarantee the operational security once we deploy QKD as a real network system. And the satellite orbit predictability introduced the critical vulnerability. At a high level, the core observation of our work is simple, but its implications are far-reaching. The low Earth orbit satellites are inherently predictable because their trajectories are publicly available through two-line element data, which is necessary for collision avoidance, tracking, and ground station scheduling. And this predictability is not a design flaw. It is a fundamental requirement for operating a satellite system at scale. But from a security perspective, this creates a system-level vulnerability that has largely been overlooked in prior work on the satellite QKD. Unlike the terrestrial fiber links, which are physically hidden and difficult to localize, a quantum satellite's future positions and the visibility windows are effectively exposed in advance. This means that the attacker does not need to guess when a vulnerable link will appear. The system reveals that information by itself. And based on this observation, we consider a targeted eavesdropping threat model. In this model, an adversary leverages public orbital data to precisely anticipate when the quantum satellite will establish a line of sight link with the ground station. The adversary then positions eavesdropping equipment within the satellite's beam footprint during the short visibility windows. And importantly, this is not a hypothetical attacker. The attack does not require breaking the quantum cryptography or exploiting the hardware bugs. Instead, it exploits a property of the system architecture, the predictability at the network level. And to understand the severity of this threat, we analyze its impact on the quantum bit error rate, or QBER. Under normal operating conditions, without any adversarial inferences, the baseline QBER in our model is approximately 4.7%. This level of error is well within the tolerable range for the integument-based QKD protocols. However, under targeted intercept, the QBER increases dramatically, reaching up to 27.5%. But for the E91 protocol, the secure key generation becomes impossible once QBER exceeds roughly 11%. This means that even partial is sufficient to completely disable secure key generation. In effect, a multi-billion-dollar quantum satellites can be rendered operationally useless without ever being physically damaged. From this analysis, we identify three fundamental challenges. The first one is how to ensure efficient QKD over dynamic satellite ground links. This is because satellite-to-ground quantum links are highly dynamic and short-lived, often lasting only a few hundred seconds per pass, and this is a very limited time to accumulate keys. And the second is how to prevent adversarials from identifying quantum satellites. Because once identified, quantum satellites becomes high value and easy targetable nodes within the constellations. And the third challenge is how to maintain QKD continuity under active attacks. This is because simply detecting an attack is not enough. We must also maintain service continuity under active adversarial conditions. And these challenges cannot be solved by the physical layer techniques alone and require the system level design in this case. So how do we address these challenges? We propose a two-layer defense framework that doesn't require changes to quantum hardware, but instead leverages the inherent characteristics of large-scale satellite constellations. The first layer is stealthy deployment. We hide the quantum satellites within the massive LEO constellations to drastically increase an adversarial search space. And the second layer is the dynamic rerouting, which is an adaptive countermeasure that re-establish QKD sessions via the alternative passes upon eavesdropping detection to ensure the service continuity. And together, these two layers transform the satellite QKD from a fragile point-to-point system into a resonance constellation scale services. Let's examine the first layer, the stealthy deployment. Our goal is to embed the quantum satellites directly into a large LEO mega constellation, making them indistinguishable from the conventional ones. And we achieve this through three key components: the orbital and visual camouflage. The quantum-enabled satellites are assigned the orbital parameters and physical profiles that match those of conventional communication satellites. And the second one is the functional obstruction, which means each quantum satellite is equipped with the conventional communication module and performs standard relay or communication tasks, and making the operational patterns distinguishable from the non-quantum satellites. And the third one is the beam overlap, which means the entanglement distribution beams are spatially and spectrally overlapped with the classical communication traffic and concealing the quantum transmission within the broader traffic patterns. And the attack problem can fundamentally change from targeting a known quantum node to guessing among thousands of virtually and fundamentally identical candidates. And then let's move on to the second framework. Despite stealthy deployments, high-frequency eavesdropping attempts may still compromise QKD sessions. To maintain operational continuity, we introduce a dynamic rerouting mechanism that detects anomalies and immediately switches the QKD sessions to an alternate quantum satellite. A unique and powerful property for QKD system is that eavesdropping is inherently detectable, and any interception introduces disturbance that manifests as an increase in QBER. And we exploit this property by continuously monitoring QBER as a real-time intrusion signal. And when the system detects that QBER exceeds a threshold, the current QKD session is immediately aborted. And the system then reassigns the quantum communication task to a pre-identified backup satellite that has overlapping visibility with the same ground station. And now let's turn to the system design. We built an integrated simulation framework for evaluating stealthy deployment and dynamic rerouting strategies. The architecture comprises three core modules: the satellite data center for the orbital dynamics and visibility prediction, the quantum simulator for the physical layer QKD protocol emulation, and the dispatch center for network coordination and the defense strategy execution. And these components operate to maintain the robust quantum communication and the dynamic network conditions and the adversarial threats. Now to our experimental evaluation. We evaluate our defense framework using a large-scale simulation grounded in real orbital data. Specifically, we use the public available Starlink PLE data coverage approximately 6,000 operational satellites. And we focus on two key metrics, the QBER, which reflects the link integrity, and the cumulative key generated, which reflect the actual system throughput. And we built a satellite ground station integument distribution simulator that faithfully replicates the full QKD workflow based on the E91 protocol. And we first explore the impact of eavesdropping frequency on secure key generation efficiency. Let's take a look at this figure. X-axis is the timeline, and Y-axis is the cumulative keys generated. It shows the total cumulative keys and the different eavesdropping frequencies during the first months of 2024. The result shows that as the eavesdropping frequency increases, the number of the successfully generated keys declines substantially, and even partial eavesdropping leads to noticeable degradation. And under the persist interceptions, the QKD channel can be rendered entirely ineffective. And here we test the performance of the stealthy deployment scenario. The result shows about how attack success rate changes as we increase the number of satellites in the constellations. X-axis is the total number of satellites, Y-axis is the attack success rate. And under stealthy deployments in constellations, the probability that an attacker successfully targets the correct satellites drops to approximately 0.016% per attempt. But even with stealthy deployments, under high attacker density, the randomized eavesdropping may succeed with non-negligible probability. To address this, we introduced the dynamic rerouting. And this figure shows how attack success probability changes as we increase the number of attackers. X-axis is the number of attacks, Y-axis is the attack success rate. When n equals 1, meaning there's only one quantum-enabled satellite, the attacker only needs to successfully disrupt the single node. However, when we enable dynamic rerouting with n equals 2, 3, or 4 quantum satellites, an attack becomes exponentially harder as n increases. As a result, the system-level attack success rate remains near zero when redundancy is present. And instead of increasing the number of attackers, we now fix the adversarial scale to 10 eavesdroppers and ask how the system behaves as the constellation grows. Here's the result. X-axis is the total number of satellites, Y-axis is the attack success rate. The blue curve shows the case with a single quantum-enabled satellite. As the total number of satellites increases, the attack success probability decreases, confirming that the stealthy deployments benefits our large constellations. And when we enable the dynamic rerouting with 2 or more quantum satellites, the attack success rate rapidly collapses toward 0 as constellation size increases. And here, we want to test the performance of the framework by the extreme stress test. When the dynamic rerouting is added, the system exhibits strong resilience even under extreme conditions. We can see this figure. X-axis is the timeline. Y-axis is the cumulative key generated. And under an attack scenario involving up to 1,500 concurrent eavesdroppers, our framework preserves nearly 70% of the cumulative key generated capacity. And this corresponds to up to a 90% improvement compared to the undefended design. In summary, our work makes 4 key contributions. We introduced the first network-level defense framework for the satellite-based QKD against the targeted eavesdropping. And we showed that the predictable orbital dynamics creates system-level vulnerabilities beyond point-to-point quantum defenses. And our 2-layer design combines stealthy deployments and the dynamic rerouting to ensure service continuity. And finally, the large-scale simulation demonstrates up to 90% improvement in the cumulative key generation under the adversarial conditions. And that's all for my presentations. Thank you so much.